To understand the equivalence between a circuit implemented in all NANDs compared to a circuit implemented with ANDs and ORs, consider this example. Here we have two AND gates with signals A, B, C, and D, and combined into an OR gate to produce this logic product, that is A and B or C and D. Now, of course, A and B can be the same signal. I mean, it could be B here and B here and so on. I'm treating them separately so that you'll see that this works for independent signals. It also works for any signals. So this is the standard sum of products notation. Down below, I have drawn the same circuit. The only difference is, on the output of the AND gates, I have inverted, and then at the input of the OR gate, I have inverted again. Now, if you invert a signal and then invert it again, it comes back to where it was. So the input to the OR part of this gate is the same as the input to the OR part of this gate, because an inversion followed by another inversion means that it sees the same signal that this OR gate saw. Therefore, the output of this circuit is also going to be A, B, or C, D. So now all we have to do is prove that an OR gate with inverted inputs is the same as a NAND gate. Down here, I have shown an OR gate with, these are the signals, these are the inputs. Now they're simply copies because in this case we are not inverting the inputs. So a simple OR gate, if the inputs are all zeros, the output is a 0. If any input is a 1, the output is a 1. Consider now what happens with the same set of signals, but instead of applying these signals, you apply the inverse. In other words, you invert this one to produce a 1, this one to produce a 1. So instead of 0, 0, 0, 1, 1, 0, 1, 1, we have for this truth table 1, 1, 1, 0, 0, 1, 0, 0. You might want to look at this a little bit if you want to pause the video and convince yourself that all I have done is taken these signals, which are the same as these signals, and inverted them into the OR gate. So now the OR gate sees these signals. Well, once again, it only produces a 0 out when both inputs are 0. And in this case, the inverted inputs are both 0 here. In the other three cases, it's a 1. Now compare that to a NAND gate. A NAND gate, once again, here are the signals. Here are the inputs. We are not inverting the inputs here. We're just copying them into the table. So now we see that for this set of signals, we get 0, 1, 1, 1, the same as we got out of an OR gate with inverted inputs, 0, 1, 1, 1. Therefore, we can say that an OR gate with inverted inputs is logically equivalent to a NAND gate. In fact, it is a NAND gate. So, what we've shown is that you can take any logic circuit, because any combinational logic circuit can be made up of sum of products. In other words, ANDs followed by ORs. You can then, from this proof, determine that if we replace this gate with a NAND gate, which means that instead of inverted inputs to an OR gate, we have the same circuit as on the left, you now have NAND, NAND, NAND gates, but it produces the same result. So another way to do this, or to say this, is to convert from AND OR to all NANDs. All you have to do is replace all the gates with NAND gates. There's a similar proof for NOR gates, but I won't go through it here. You might want to try it yourself using the same procedure. So I think we have now reached a point where you have a knowledge of combinational logic, which is roughly equivalent to the first half of a semester in logic design that is studied at a college level. If you followed through to this point, you should be proud if you had no logic experience to begin with. If, on the other hand, you had some logic experience and you have followed through to this point, you can be assured that you're now back up to the speed you had when you got out of that logic design course with respect to combinational circuits. So I'm going to go ahead and put the series together and post them on YouTube as a set of computer logic videos. At some point in the future, I will probably pick up this series and continue with a set of videos on sequential logic. Once again, I hope you've enjoyed this, and I hope you'll stay tuned for some future videos. So have a nice day.